Okay, let's get started. We are glad to have Ettore Minguzzi from the University of Florence, who is a recipient of the Frontier of Science Award. His title is a proof of the consistency of surface gravity for non-degenerate complex horizons. Let's welcome.
Thank you. Thank you to the organizers, first of all, for the organization of this amazing Congress. Yes, I'm going to talk about this proof of the constancy of central gravity in the non-degenerate case. And I will give briefly some context, but most of the talk will be about some details of the proofs that I think are themselves curious and interesting. Then I believe more content will be given in the next talk by Bustamante. So this is not more. Okay. This way. So motivation comes from Penrose strong cosmic censorship conjecture that roughly stated that under reasonable physical assumptions, that is, geodesic condition and energy conditions, space-times have to be globally hyperbolic. Although usually formulated in a PDE context with the use of vacuum Einstein's equations, this is a statement about generic space-time, so non-empty space-times. Among the implications, if the conjecture is true, then also compact Cauchy horizon should not form under reasonable assumptions. So suppose that the energy conditions are true and that the spacetime is vacuum and that, however, there is a compact Cauchy horizon. Then the assumption, this hypothetical cosmic censorship, should fail. That is, that there should be non-generic. And so we expect from cosmic censorship that if there is a compact Cauchy horizon, then the spacetime must be special. How to formalize this set of beliefs? Through this conjecture in which by Isenberg-Moncrief, in which the idea of being special translates in the existence of a killing field. So the conjecture states that for every smooth, compact, null hypersurface, so generated by like geodesics, in an electrovacuum spacetime, any such hypersurface is actually killing. That is, there exists a killing vector field tangent to the hypersurface. Now, to give you something a picture to think while we progress with the talk. Imagine a strip from Minkowski 1+1 spacetime. In Minkowski, you have the cones that are all translational invariant. These are the future cones, and the times progress from bottom to top, increases in this direction. Now imagine I take this strip, identify, and furthermore, I change the metric, tilting the cones. So they start to tilt at some point and become horizontal at some point. Then what happens is that here in this region, we have closed time-like curves. So there will be a region such that through every point passes a closed time-like curve, because via the identification, I can go back and then return, forming a closed time-like curve. If I start from a Cauchy hypersurface S, the Cauchy development cannot include this region. I don't know where the region starts of chronology violation, but there will be some point where it will start. So there is some other surface here, which is the horizon of S, such that the region from S to the horizon is domain, is the Cauchy development. Is the wave equation or other field equations can be developed from data starting from S up to a certain point called horizon. Now, so the talk is it's about this type of object. This figure happens to be compact, okay? And we want to prove that to study their geometry. Isenberg-Moncrief were able to prove the results under some assumptions. That is this conjecture. It is that the metric and horizon are analytic, and that the generators are closed. That is what happens. You see, I can follow here electrolyte generators as the cone tilts, also the generator tilts. And the generator will approach the horizon. In fact, the horizon will be generated by light-like geodesics. So this curve here in this drawing is actually a light-like geodesic. But in more than two space-time dimension, there is a problem that this set has more dimensions. So for instance, if I were to focus just on this set here, this would be a set run through by light-like geodesics. Here we shall have some sort of identification. It will be compact, but depending on the dynamics of these generators, it can be that don't close. Okay, so there can be many distinct generators that accumulate on themselves or that present a complicated dynamics. So under the assumption that the generators close and that the horizon is analytic, they were able to show that actually in a neighbor of the horizon, there is a Killing vector field. And that this Killing vector field is tangent to the horizon. So there is a Killing vector field K tangent to the horizon. This is the statement. Now, in particular, there is this definition of surface gravity. That is, if we put here a field n of electric vector field that is tangent to the generators, we have many choices to make this, to introduce this vector field. Because these are like vectors, there is not a privileged scale. We cannot normalize them, so we can make many choices. They are going to be not geodesic, but because they are not going to be finely parameterized. This is a typical problem in relativity. If I start with the geodesic, I propagated the geodesic. If it closes, when I come back here, the tangent to the geodesic gets dilated or shortened. This is related to the fact that the geodesic is going to be incomplete or complete. So in reality, we cannot introduce a tangent vector field in such a way that it is a geodesic field in general. What we can do is we choose first a tangent vector field, which is like, and we see what equation it complies. And the equation is a pre-geodesic equation where there is a function kappa, not to be confused with k, which is the Killing field when there exists. So this kappa in general is a function, and this function is called surface gravity. Now, it is known that if the field is a Killing vector field, that is, if the horizon is a Killing horizon, and this tangent is n is actually a Killing vector field, then that surface gravity is a constant. This is a classical result. So since they show that the horizon is Killing, in particular, they show that taking with the n the Killing vector field, that the surface gravity can be normalized to a constant. Normalized means I can choose a tangent vector field such that kappa is a constant. And then they prove other things, for instance, that in electrovacuum spacetime and under other assumption, okay, surface gravity can be normalized to a constant. And then they distinguish two cases. The case in which they get zero surface gravity and the case in which they get non-zero surface gravity. And prove that in the non-degenerate case, all the generators are complete in one direction and incomplete in the other. The horizon is actually a Cauchy horizon, that is, it comes from a boundary of the Cauchy development of the Cauchy Eppert surface. And the Killing field is space-like on one side in the global hyperbolic region and time-like on the other side. Instead, in the degenerate case, they get that the generators are complete in both directions, and the horizon in general need not be Cauchy. So, since that time, there was this problem, which is the Isenberg-Moncrief conjecture, of showing that conclusion do not depend on the assumption of analyticity of the horizon and on the assumption of closure of the generators. So the first step in this program is to prove that you can find a vector field tangent to the horizon such that surface gravity is constant. The reason is that in reality, it can be shown that if the surface gravity is constant, the derivative of the metric on the horizon is zero in direction of the generator, which is what we expect from a Killing field. In practice, then the problem becomes a problem of PDE. Once you have shown that the derivative of the metric on the horizon is zero, you use some sort of wave equation to extend the property outside the horizon and create a Killing vector field in a neighborhood of the horizon. But this is, so it's like creating the initial condition of this PDE problem. Now, there is an important relation with the stationary black hole. It is known that every stationary black hole has an event horizon with the same regularity as the metric, with some assumptions. And Friedrich, Rax, and Wald established that there exists a number tau such that the generators of the horizon are sent to themselves under the tau map flow of the Killing vector field. That is, I have a Killing and the map, if this is a geodesic, I would send, I pick a point, phi tau sends me to a point that still belongs to the geodesic from which I started. And so if we do the quotient with respect to this map with this precise choice of tau, the horizon that normally for a black hole, the horizon is non-compact. The horizon under the quotient becomes a compact set. And so, as a result, you can apply the techniques for compact horizon to this compactification and get results for stationary black holes. For instance, the existence of constant surface gravity. Now, in fact, the concept of constant surface gravity was created in the context of black holes, because it is the temperature, physically, of the horizon. It's related to kappa, is related to the temperature over 2 pi. So establishing that the constant surface gravity is constant means establishing that the temperature of a stationary black hole implies that the temperature of a stationary black hole is constant, which is the zeroth law of thermodynamics of black holes. So there were this approach has been used, for instance, by to show that there is this extension of Killing vector field near the horizon of black holes. This was also studied first in the analytic case by Hawking, and then without analyticity assumptions by Alexakhin, Ionescu, Kleinerman, and Petersen. Petersen used this quotient approach. And this technique that we are going to use is this, come from this paper by Moncrief and Isenberg, which is the ribbon argument that we'll show later. And with that, they obtained some results. They were able to drop the closure of generators, but still they had to assume analyticity and some transversality conditions to obtain some of the results they got before in the non-degenerate case. So there was some slow progress, but in the last year came basically all the proof we needed in the non-degenerate case. First, Reiris and Bustamante proved that in the non-degenerate case, the surface gravity can be normalized to a constant. And then Petersen and Rax proved that it can be extended in a neighborhood to a Killing field. Yes, okay. In the we have seen that in the analytic case, it was first introduced with the sign of this surface gravity that it would, but then they proved that it is equivalent to the fact that the generator is that there is a generator inextendible in the future, and this has become the definition in the smooth case. That is, non-degenerate means there is a generator which is incomplete in the future. It has to do with the incompleteness of one generator. The degenerate case is that in which all generators are complete. So what we did was to obtain a neat proof of this fact, and also to extend to non-vacuum case by using the dominant energy condition. Also, our proof does not depend on coordinate methods. That's some advantages. So let's start with the energy condition. First, we recall that this convention, vector is time-like if its square is less than 0, like if it's 0. And a vector is causal if it is time-like or like. The null energy condition or convergence condition is this one, Ricci contracted with a null vector is larger or equal to 0. The dominant energy condition can be expressed in this form that basically says that this combination of scalar curvature and Ricci, when it acts over a time-like vector, it returns a causal vector. And is stronger than the null energy condition. Now, we shall need the notion of null hypersurface. In the C2 case, it is known that an hypersurface is null if and only if it is locally achronal. That is, if you pick a point, there is a neighborhood such that you cannot find a time-like curve joining two points of the hypersurface, and generated by like geodesics. That means that in one direction, a geodesic stays interior in the hypersurface. This property is then used to define what a C0 past null hypersurface, which is also called null horizon, is. Via these properties. So in general, horizon can be very irregular. This is known from work by Cauchy and Galloway. They've shown that even if they are Cauchy, they can be non-differentiable in a dense set. And the request of being compact does not help. There are examples of space-time in which you have a compact non-differentiable horizon. Non-differentiability of horizon is related to the fact that the generators escape the horizon in one direction. If instead the horizon were differentiable, then the horizon would stay in the hypersurface in both directions. But fortunately, we proved this result that tells you that if you impose the null convergence condition and you start from any C0 compact future horizon that in one direction have incomplete generators, is as smooth as the metric. And furthermore, it is totally geodesic and run in both directions by inextendable generators. Also, the fact that the generators are complete in one direction follows from the fact that it is a Cauchy horizon. This is also a generalization of a theorem by Hawking that used the smoothness assumptions. So essentially, this proves that when a compact Cauchy horizon forms, it's going to be smooth, which is very helpful and will be used. So we are interested in hypersurfaces that have the same properties of the hypersurface implied by the previous theorem, though they are not necessarily Cauchy horizons. We want them to be totally geodesic, null hypersurfaces, compact, smooth, and so on. N is going to denote the vector field tangent to it for a given choice. And the total geodesic property means that the expansion and the shear are zero. As it is zero, the Ricci contracted with the tangent to the horizon. Now, as in Lorentzian geometry, if you are given an hypersurface, you have also the definition of shape operator. You take the normal vector and you take the gradient. This is going to be linear with respect to x. But this time, the normal vector is tangent, because for a light-flat hypersurface, the vector, which is normal to the hypersurface, is actually in the tangent to the hypersurface. So, in reality, one has to, the definition of shape operator is a bit more complicated. We need to take the quotient. After you take the derivative, you take to send to zero the terms that are proportional to n. And then the total geodesic property is equivalent to saying that this B, which is the shape operator, is zero. So what we have shown, and that the compact Cauchy horizon satisfy this property here. This nabla of x, where x is tangent to the horizon, is going to be proportional to n. So the coefficient in front of it has to be linear with respect to x, and so it's going to be a one form. So automatically, being totally geodesic implies that there is a special one form on the horizon, which is this a form that we call omega. Then if we put n in place of x, we see that we get here omega n, and this is kappa, surface gravity, because this would be the geodesic equation, nabla n equal kappa n. So kappa, the surface gravity, is omega n. Now, so the question is, we are going to denote lambda of a point P as the affine length of the geodesics that start from P with tangent n. Okay? We make a selection. We choose a tangent vector field n to the horizon. We pick a point P. We consider the geodesics that start with velocity n and denote with lambda p its affine length in the future. As I've stated, it need not be complete because of this effect that even if it were closed, the tangent vector gets dilated every time. So the affine length, it's a sum of affine length that gets shorter and shorter because the tangent vector that gets bigger and bigger. Null geodesic, yes. The generators are all null geodesic. N is a like vector. Okay, this is a zoom. This is the horizon. I took the horizon, it could be F dimension 2, and moved it this way to show you the generators running through the horizon. In this picture, is one dimension and you will not be able to see it. In practice, you need to add the dimension here. And here you have the generators running through the horizon that then get identified. And these are like. So now if we rescale the vector field n with a certain function, we get another choice. And this is how all the quantities introduced before change. The one form omega, the affine length, and the surface gravity change in this way. So suppose that we knew that lambda is smooth and finite, something that we don't know. But suppose we knew that. Then if we choose this exponential in this form equal to the affine length, then replacing here, we will get that the new affine length is 1. Okay? And this, we will see in a moment that this is equivalent to have constant surface gravity. That is, constant surface gravity is equivalent to say the affine length of every geodesic is independent of the starting point. In fact, if we write, if we take a generator and we are going to calculate, we put a parameter tau over these generators. For every tau gives me the starting point that I choose, and then I calculate the affine length starting with of the geodesic that start from this x tau in the future. Its expression is given by this formula here, where kappa is the surface gravity. Then we see, it's easy to see with the computation, that it satisfies this equation. If lambda is a constant, then we easily find that lambda is, this goes to 0, and so you can recover kappa from here, and you get that kappa is a constant. So, if we can show that lambda is smooth and finite, we can make a gauge transformation such that lambda become a constant and kappa become a constant. But the problem is to show that lambda is smooth and finite, something that we do not know. So we're going to follow, we're going to make two steps. The proof goes in 2 steps with 2 gauge transformations. In the first gauge transformation, we prove that we can bring the surface gravity to a negative value, still a function, but a negative value. We don't know yet that lambda is finite. Sorry, this is k prime. Then, since k prime is negative, this implies that lambda prime is finite by the formula above. That is, if here we know that kappa is negative, then everything converges and lambda prime becomes finite. And also we are able to prove that it is smooth if I have this kappa negative. And then at this point we do the second gauge transformation as we have shown before, and we get surface gravity normalized and affine parameter normalized. Now, if we use the, if we use the totally geodesic assumption, it's easy to see from the definition of curvature that we are able to prove the first formula, in which, here in these steps I use the definition of omega, in which there appears the stereo differential of omega. And also we get a similar formula for Ricci. In particular, the second one, it's important because by using, if you assume the dominant energy condition, if Ricci of xx were 0 from some like vector, then we can infer that this Ricci of x is also this one form is also proportional to g of x. This follows from essentially the equality case of the reverse Cauchy-Schwarz inequality, which is reverse because it holds in the opposite sign in the Lorentzian signature. Essentially, one shows that x, the scalar product of x with the image of x under the stress energy tensor is 0. But x is like the image of x and with the stress energy tensor is causal. In general, if you take the scalar product between a causal vector and electric vector, this is going to be different from 0, unless the two vectors are proportional. And this is precisely what we get. But then, if this property holds, then from the formula before, if Ricci is annihilated by n, then d omega is annihilated by n, which is the main property that we're going to use. So the stereo differential of this form omega is by the dominant energy condition is going to be annihilated by the generators. Okay, let's skip that. Also from Cartan magic formula, we find that the Lie derivative of omega is the stereo differential of the surface gravity. Another result that one can easily get using total, the fact that the Hepburn surface is totally geodesic, is the fact that if you consider the induced metric on the horizon, this is going to be degenerate, but still it shall have a Lie derivative along the generator which is 0. So now we use this trick. Over the horizon, we put a distribution of horizontal, we call them horizontal plane, transverse to the vector field n. And we make this assumption. One of our problems is that, in general, as you can see from this formula, the Lie derivative of omega a priori is not 0. It would be 0 if the surface gravity were 0, which is what we want to prove. But the Lie derivative of g is 0. So the idea is, let us consider this ratio, omega x over square root of gxx, where x is horizontal. The horizontal bundle, this bundle that we have seen here, if you take the projectivized horizontal bundle, is going to be a compact manifold. Over this compact manifold, this ratio is non-zero. And so it has a maximum. And so from that you get that there is this constancy, which proves this lemma. Now we arrive at the main idea, which is the idea of ribbon, which is due to Isenberg-Moncrief and improved by us. That is, we consider, we have said that we have a distribution here of plane. We take an horizontal curve and we consider two horizontal curves that are homotopically related. So the longitudinal curves are called gamma 1 and gamma 0. And the horizontal curves are called sigma 0 and sigma 1. Now, if you use Stokes' theorem, by using this form omega, the exterior derivative is going to be 0 because it is annihilated by n, which belongs to the horizon. So we get this equality. However, this integral, in the terms that it is horizontal, that is this piece here, we have two pieces horizontal, this one and this one, is actually bounded by a constant which is independent on how much elongated is the ribbon in the future. That is, if we elongate it, now suppose we have the identification, however, I don't identify to don't mess up with the figure, I can elongate it and get another curve, or elongate it again and get a different curve. But the integral of omega has always the same bound. Why? Because omega is bounded by g, and g, it's invariant under the flow. This is the idea. But then, this means that the integral of gamma on the longitudinal curves of omega, we have an error, which is this bound on the horizontal pieces, that stays always the same, independently on how much elongated are the curves. And so, these geodesics, the idea is that I push the geodesics to infinity and calculate this integral of omega along a geodesic, and I can compare it with the same integral on another, starting from another geodesic. And these two numbers, if one goes to infinity, the other must go to infinity. If one oscillates, the other must oscillate, and so on. If one is bounded, the other must be bounded. So if the integral of a future generator starting from P converges to minus infinity, the same happens for every generator, okay, and all the other behaviors. Now, this integral is related to the incompleteness of the generators. Let's show that. First, there is an observation with through a couple of lemma. You remember that we have a precise expression of what is this affine length. This affine length is essentially this integral here. And the integral of omega along the generator, since the generator are tangent n, omega evaluated with n is the surface gravity. So this integral of omega is the integral of the surface gravity, which is precisely the one that appears in the expression for the affine length. So if this integral goes to infinity or to minus infinity for one generator, it goes to minus infinity to another generator. And we are able to show that this implies that if one generator is incomplete, the other is incomplete. And every generator is incomplete. No, I don't. So assume that there is a generator such that now, through a compactness argument, now that we know that this integral, suppose that there is one incomplete, and so this integral is minus infinity for every generator. Then via compactness argument, we find that there is a constant C such that if I integrate omega, I know that if I integrate from 0 to plus infinity, I get minus infinity. Well, we can say that there is a constant C such that if I integrate up to constant C or more, the integral is going to be negative. This is obtained via compactness argument. But then the idea is, okay, then what I do a gauge transformation in which the function f is obtained via this integral, which is finite. That is this s, which is an integral variable, is not going to 0 to plus infinity, and I cannot control. It's going to be up to a certain constant, which is finite, that I found from the previous lemma. And then via an algebraic calculation, this shows that K prime, the new surface gravity, is going to be strictly negative. Still a function, but strictly negative. At this point, what it follows, again from the, choosing this as gauge, this is, I change vector field, I put myself in the new vector field that I know exists, that has negative surface gravity, I calculate the affine length, and I get, because this is an exponential which is negative, kappa is less than certain constant because we are in a compact set. It's a function that is negative, it's bounded from above by a negative constant, and so this converges. So affine length is finite. And it remains only to show that it is smooth. And then we can apply the last gauge transformation and solve the problem. And, well, essentially, the proof can be done in two ways, depending on whether you assume that you have vacuum or not. If you have not vacuum, you can do it by induction, by calculating the derivatives and showing that you always get a certain expression with a polynomial. And since this is essentially an exponential, surface gravity negative constant, this is a typical a to the minus something linear in S, these always converge. And you can show that this step in taking the derivatives is well defined using the dominant convergence theorem. Or if you are in vacuum, you can even, after some calculations, show that actually in vacuum you get a partial differential equation, which is this one, B is 0. B it's a function that is a certain integral related to the logarithm, well, to the Ricci tensor. If Ricci is 0, all this B is 0. And what you get is a second order partial differential equation on lambda, capital lambda, which is the affine length. Eta is a quantity that depends on smoothness elements of the curvature. Omega is the form we saw before. So this is the Hessian of lambda, and here by bootstrap you conclude, first by hand you prove that it is C1, C2, and then by bootstrap with this equation you conclude that it is smooth. And so this complete the proof. So assume the dominant energy condition and that there is a future incomplete generator, then the smooth vector field can be chosen such that the surface gravity is -1 and the affine length is always 1. This also allows to define what does it mean to be non-degenerate. It can be given with several equivalent property definition. The horizon emits a future incomplete generator. There is a smooth vector field that has negative surface gravity, but still a function. Or there is a smooth vector field that has surface gravity, which is a negative constant. Or for some choices vector field, there is one generator such that the integral of surface gravity along the generator is diverges to -infinity. These are all equivalent. In particular, you get that for a future in the non-generated case, all generators are complete in the past direction and incomplete to the future, and dually in the reversal time orientation. Or for a degenerate horizon, they are all complete. And now I don't have much time. I just want to mention that one thing one can do is then study a little what happens in a neighborhood of the generator, the horizon. And then what one sees is that in the non-degenerate case, you can pick a field transverse to the horizon, and then if you push in one direction, you enter the region of chronology violation. That is, we started from a generic compact horizon, not from this construction. But this construction I presented you in the beginning, turns out it is general. If the horizon is non-degenerate, on one side you have chronology violation. As you move up, you enter the chronology violating region. If you go down, you create a Cauchy hypersurface was horizon is the horizon you started with. And this is the content of this theorem. So that's all. Thank you.
Not making an assumption about dimension, I understand. So this is no dimension.
Yes, this is in any dimension.
And if we assume that the metric is smooth, you can probably go with symmetric C3. What's the threshold?
Okay, the theorem we start with that proves that every Cauchy horizon is actually smooth as the metric works if the metric is C3.
And then you can continue from there?
And then everything works, yes. No, it's not...
Of course, the open question is kappa equals 0.
Yeah, right now that's what remains to do. Almost every argument fades in the kappa equals 0 case, so the Isenberg-Moncrief conjecture is open in the degenerate case, which corresponds to the extremal case for black holes. The extremal case is open, yes. But we have some results. Not in the most general case, but some results we have.
Can you expand on what you can prove now?
Yes, if the generators are an S1 bundle, we can prove it. If the generators are many general, so far not. But in general, if the black hole is not a problem, because the case of the black hole, when you take the quotient, the bundle we can show that is trivial. It's an S1 trivial bundle. The dynamics of the generator is very simple, and the degenerate case works.
But this is in n equals 3, right? I mean, space dimension 4, or is it?
It's independent of
the
dimension.
Right.
And yeah, if there's a strong point of censorship, how it's related?
Yeah, because the strong cosmic censorship is what allows to do analysis in relativity. That is, we start from a Cauchy-Shepard surface and we evolve things. But if the Cauchy-Shepard surface does not hold, then by doing analysis, you would only know the region of space-time that is developed from the Cauchy-Shepard surface. The space-time might continue beyond the Cauchy horizon, and you will never know it by evolving data. That is, the solution of the Einstein equations do not necessarily have the property that they are globally hyperbolic. That is, the space-time that you get as the maximal extension of curved space-time present closed time-like curves. But you don't see them if you evolve from a hypersurface. In fact, that hypersurface is not a Cauchy hypersurface, it's a part. It should be called in a different way because the Cauchy development is not the whole of the spacetime. The spacetime is not globally hyperbolic. So the idea that in reality, by evolving the data in the hypersurface, you get the whole spacetime, that's the cosmic censorship. That's what you are asked to prove that you cannot extend the spacetime beyond the horizon. So the first thing you need to do to prove something like that is to study horizons, to exclude that they exist. So if the horizon is compact, is the simplest possibility. You say, okay, let's assume that the horizon is compact. I want to know everything about this spacetime with the compact horizon. I bet that this spacetime is very special, and there should be a killing. This is the conjecture that has been proved.
Amen.